It's finally time to put everything we've learned about coordinate systems and surfaces to use. So let's start with a quick revision of the different types of integral we've seen so far. A classical integral in one dimension gives us the area under the curve between the endpoints A and B, and the fundamental theorem of calculus tells us that if the integrand has an antiderivative, then the integral is found as the difference in values of the antiderivative at the endpoints. We've seen that this can be generalised to two dimensions to form what we call an area integral. Here we have a function of two variables defined over some subset of R2. If we plot this function as a surface on the z-axis, the integral represents the volume under the surface. Note that we call it an area integral because the domain is an area, but the result is actually a volume. To do such an integral, if the integrand is continuous, then it can be done as an iterated integral, specifically a double integral, meaning that we do the integral over x, holding y constant, and then we do the integral over y afterwards. Fabini's theorem tells us that if the integrand is continuous, we can just as well do the other way around, i.e. we can do the integration over y first and then x, and we'll get the same answer. Furthermore, we aren't restricted to using Cartesian coordinates. If it's easier to do so, we can change to polar coordinates, or indeed any other 2D coordinate system. So now we move to 3 dimensions and form the volume integral. This is where we have a function of 3 variables and the domain of integration is a volume of 3D space. We can't really draw a picture for this one, but in theory, imagine we used the x, y and z axes for the domain of the function and a 4th axis for the output. The graph of the function would be a hypersurface in 4D, and the result of the integral is the hypervolume under this hypersurface.
Okay. Can you repeat the part of the stuff where you said all about the things?
Anyway, it essentially means we are summing the values of the function across the 3D domain. Again, provided the integrand is continuous, we can do it as 3 iterated integrals, a so-called triple integral. And Fabini's theorem says we can do it in whatever order we like. Again, Cartesian coordinates may not always be ideal, so if it helps, we can use cylindrical coordinates or spherical coordinates instead, or indeed any other 3D coordinate system. Let's just note again that when we say area integral or volume integral, we're referring to the domain of the integrand, not what we actually obtain after the integration is done. As was the case with area integrals, the hard thing about volume integrals is often not the integration itself, but first of all determining the appropriate limits for the iterated integrals. So let's look again at how we did that for area integrals in Cartesian coordinates. Suppose we do the integration in the order y first, then x, which means that the integral over y is nested inside the integral over x. We have to think about some particular value of x and figure out the lower and upper values of y here. But the thing is, if we then move to a different value of x, the lower and upper values of y can change. So what we actually have to do is find 2 functions, y1 of x and y2 of x, that give the lower and upper values of y for any particular value of x. And these functions of x are what we put as the lower and upper limits on the integral over y. Then for the outer integral over x, the limits are just constants, the lower and upper value of x. On the other hand, if we do the integration in the other order, that's x first and then y, then we have to find 2 functions x1 of y and x2 of y that give the lower and upper limits of x for any particular value of y, and use these as limits on the inside integral over x. So when we move to 3 dimensions where the domain of integration is now a region of 3D space, things quickly start to get quite technical. In 2D there were only 2 orders we could do the integration in, x first then y, or else y first then x. But in 3D there are 6 different orders: xyz, xzy, yxz, yzx, zxy, zyx. So let's just pick out one of these orders and see how the limits of integration would be determined. Let's go with z, then y, then x. If we want to use this order, we have to find 2 surfaces, z equals z1 of xy and z equals z2 of xy, in explicit form with a common domain in the xy plane, where z1 is the lower bound of the volume and z2 is the upper bound of the volume. z1 and z2 will be the limits of the innermost integral over z. Then we need the domain of the functions z1 and z2 in the xy plane. So we have to find functions y equals y1 of x and y equals y2 of x that are the lower and upper bounds for the y values, and use these as the limits on the integral over y. Finally, we need the lower and upper values of x for the limits on the x integral. These are just constants. This is always the case with area integrals or volume integrals. The outermost integral always has constant limits. In general, the limits on each integral are functions of the variables that remain to be integrated over. If we choose to do the integral in a different order, we follow the same logic but interchange the roles of x, y and z. So, let's do an example of a volume integral. Suppose we're asked to find the integral of 1 minus z squared over the volume V, which is the volume inside the square-based pyramid shown. Let's suppose we choose to do it in the order x first, then y, then z. So, first we have to find two explicit surfaces, x equals x1 of yz and x equals x2 of yz, that bound the volume in the x direction. The lower bound is just x1 of yz equals 0, which is highlighted here in blue. The upper bound is the triangular face at the near side of the diagram. It's a portion of the plane x plus z equals 1, so rearranging this gives x2 of yz equals 1 minus z. So now that we've got the x limits, we need the y limits next. Looking at the blue triangle in the yz plane, for a particular value of z, y can vary between 0 and 1 minus z. So these are the limits for the y integral. Finally, z varies from 0 to 1. The actual integration is then carried out as shown. You could pause the video and read through it at your own pace. The final answer is 3/10. Another example. We want to find the integral of z times e to the x squared plus y squared over the volume on the inside of a cylinder of radius 2 between z equals 2 and z equals 3, where the outer wall of the cylinder has the equation x squared plus y squared equals 4. Let's try to do the integration in the order z first, then y, then x this time. The surfaces z1 of xy and z2 of xy that bound the volume in the z direction are just z1 of xy equals 2 and z2 of xy equals 3. Then the common domain of z1 and z2 in the xy plane is the circular disc highlighted in blue. For a particular value of x, y varies from minus the square root of 4 minus x squared to plus the square root of 4 minus x squared. Finally, x goes from minus 2 to plus 2. We quickly run into a problem though. We can't actually find an antiderivative of e to the x squared plus y squared with respect to x. Well, to be more specific, the antiderivative does exist, but it can't be written using elementary functions. It turns out though that we can do the integral quite easily if we switch from using Cartesian coordinates to using cylindrical coordinates. The fact that the volume is literally a cylinder should sort of make that obvious. So in the integral we replace x by rho cos phi and y by rho sin phi. Rho will go from 0 to 2 and phi will go from 0 to 2 pi. Remember also that the volume element dx dy dz doesn't just become d rho d phi dz, but rather rho d rho d phi dz. That's the expression for the volume element in cylindrical coordinates. So our integrand is now just z times e to the rho squared times rho. In a case like this, where the integrand is a product of separate functions of rho, phi and z, we can actually just break it down into the product of three separate integrals as shown. So the details of the integration are as shown here. The final answer is 5 pi over 2 times e to the 4 minus 1. Okay, so now that we've seen volume integrals, we're going to move on to the concept of surface integrals. Now, on the one hand, it seems like this should be simpler than a volume integral. After all, a volume is 3D, but a surface is only 2D. But hang on, haven't we already seen 2D integrals? Didn't we call them area integrals? Yeah, but a surface integral is a bit different. Let's go back to the integrals we've covered so far. Once again, a classical integral is one-dimensional, since we have a function of one variable integrated over a 1D interval. An area interval is 2D, since we integrate a function of two variables over a 2D area. A volume integral is 3D, since we integrate a function of three variables over a 3D volume. But there's another kind of integral we've already seen that doesn't exactly fit in here. I'm talking about a line integral. This is where we have a function of two variables, like we do with an area integral, but we only integrate it over a 1D curve, like a classical integral. The value of this integral represents the area under the surface above the curve, so a line integral is kind of 1.5 dimensional, a function of two variables integrated over a one-dimensional curve. To actually do a line integral, we have to parameterize the curve, and then it does just actually become a classical 1D integral. Also note that we have two types of line integral, a scalar type and a vector type. A surface integral is a bit like this too. It's where we take a function of three variables, like a volume integral, but integrate it over just a 2D surface, like an area integral. So it's sort of 2.5 dimensional. To actually do it, we have to parameterize the surface, and recall what we saw before about finding the surface area element ds on a parameterized surface. Once we do the parameterization, it does actually just reduce to an area integral. And again, there are two types of these integrals, scalar and vector. Note with the vector type that the vector surface area element ds is normal to the surface and it could point in either direction, so we have to specify which direction we're talking about when we do such an integral, hence why there's a plus or minus sign there. An example. Suppose we want to find the integral of the function xy over the surface S, where S is the portion of the plane x plus y plus z equals 1 in the first octant of space. So S is just a triangle, as shown here. Since the equation of this plane can be written as z equals 1 minus x minus y, we can parameterize it as simply x equals u, y equals v, z equals 1 minus u minus v. We need to carefully work out the domain of u and v values, which is what the bottom diagram here illustrates. For a fixed value of v, u varies between 0 and 1 minus v, and then v itself varies from 0 to 1. So, by finding the partial derivatives of the position vector of a point on S with respect to u and v, taking the cross product times du dv, and then taking the magnitude of this, we find that ds equals the square root of 3 du dv. Thus, our surface integral simply becomes the square root of 3 times the integral from 0 to 1 of the integral from 0 to 1 minus v of uv du dv. And all of the steps are shown here. The final answer is square root 3 divided by 24. Another example. This time it's a vector type surface integral. We want the integral of a dot ds, where a is the vector field I plus zj plus 6xk, where the surface is part of a sphere of radius 3, where x is less than or equal to 0, but y and z are greater than or equal to 0. We're also told to take ds pointing inwards, because remember that in general there is an ambiguity with ds, hence why we have the plus minus sign in the expression for it. So, since the surface is part of a sphere, it seems sensible to use spherical coordinates to parameterize it. On the surface we just have r equals 3, so the parameterization is simply x equals 3 sine theta cos phi, y equals 3 sine theta sine phi, z equals 3 cos theta. We only want the part of the sphere with z greater than or equal to 0, so theta, the polar angle, just goes from 0 to pi over 2. And since we want x less than or equal to 0 and y greater than or equal to 0, this means we're in the second quadrant of the xy plane, so phi, the azimuthal angle, goes from pi over 2 to pi. By considering the directions of the vectors dr by d theta and dr by d phi, remembering that they point in the directions of increasing theta and phi, it can be seen that dr by d theta cross dr by d phi actually points out of S. So we will need to choose the minus sign in the expression for ds to make it point inwards. So again, I've shown all the steps on screen for you to work through yourself. The final answer is 9 upon 5 plus pi over 4. The final things we need to know about are Gauss's divergence theorem and Stokes' circulation theorem. We're not going to look at examples of these here, we'll just state the theorems. The divergence theorem applies when we have a closed surface, S, with a volume V inside it. If we need to do a vector type surface integral of a dot ds, then the theorem lets us transform this into a volume integral of the divergence of A. Even though the volume integral is 3D, it's often easier to compute it in practice than the surface integral. Stokes' theorem relates line integrals to surface integrals when we consider a closed curve that bounds a surface. If we want the line integral of a dot dr around the curve, the theorem says we can also do it by taking the integral of the curl of a dot ds over the surface, taking care about the directions in which we go around the curve and of ds. So that's the end of our study of coordinate systems and volume and surface integrals. I hope you found these revision videos useful.
Good luck. You're gonna need it.